So, now we are going to start the second unit and that is on surfaces in R3. So, the idea of surface all of you have. What I will be telling you now is how to visualize a surface in R3. So, first look at geometrically. Suppose I give you a closed rectangle. This rectangle is a subset of R2. If you pick it up and deform it, and this deformed shape of this rectangle will not be a object inside a plane, it will be an object inside R3. So, it will look like this kind of shape. So, what you did mathematically, that you took a sheet of a surface, sheet of a plane sheet, and then you applied some function on it, and that function is a deformation, and that gives rise a surface. So, now if I put it in a more formal language, then a surface or a simple sheet of a surface, to be more simple, a simple sheet of a surface in R3 is a set of points in R3 which has a 1:1 continuous correspondence with points of a rectangle in a plane, of course. A simple sheet of a surface in R3 is a set of points which has a 1:1 continuous correspondence with points of a rectangle in a plane. So, this I am demanding it should be continuous function and it should be 1:1. So, if you map the points of a rectangle into R3, then you will be getting a simple sheet of a surface. If I drop the requirement of 1:1, then I will call the objects to be simply a surface. Okay. So, now what will happen that if I take a point on this sheet, then this must be a vector in R3, because this object is lying in R3. So, this is a vector which lies in R3. So, the position vector of every point on a simple sheet of a surface is a vector, and this vector will be a function of two variables u1 and u2, where u1 u2 are coming from this rectangle. This rectangle is nothing but it is in fact an interval a b, you can take close also, or an c d. If you take the product of two closed interval, then the shape that you will be getting in R2 will be a closed rectangles. So, what I am saying is that u1 is varying on the interval a b, whereas u2 is varying on the interval c d. So, an arbitrary point in the rectangle will be u1 u2. This u1 u2 will be mapped under the continuous 1:1 function to a point of the surface. So, the position vector of the arbitrary point of the surface will be a vector valued function. So, this is a vector valued function. So, this is vector valued continuous one to one function. So, from the definition, the equation of a surface emerges as, so this implies from the above discussion, the equation of a surface is R equal to R of u1 u2, where u1 u2 are called the parameters of the surface and they are varying over certain intervals. So, u1 varies over interval a b and u2 varies over some other interval c d. All right. Now, R is a position vector of an arbitrary point. So, it must have certain components. In fact, it has 3 components. So, the vector of the right side will have 3 components x, y and z. These are the 3 components of the vector R. R is depending on u1 u2. So, each of its component will also be a function of u1 u2. X is a function of u1 u2, y is a function of u1 u2 and z is also a function of u1 u2. So, R will look like this in terms of its component. Okay. Now, for doing geometry on a surface, I will assume that this surface is a differentiable, this function must be differentiable, not only continuous. In fact, I will be assuming it will be a differentiable function, differentiable of class C n. So, there is definition of regularity. So, a surface is said to be a surface of class C n, a surface is said to be of class C n if this vector valued function admits derivative up to order n, all partial derivative, if the vector valued function admits derivative, partial derivatives up to order n. And okay, up to order n, and the derivatives, partial derivatives, the partial derivatives are denoted by the following notations. So, if you did partially differentiate r with respect to u1, the symbol will be r1. If you differentiate r with respect to the second parameter u2, you will be denoting this by r2. r1 and r2 are vectors themselves, and how they look like, this I will be discussing little later. Now, if I impose one more condition, that the cross product of r1 r2 is non-zero at a point P, we will call that point of the surface to be a regular point. A surface of class C n, a point P on a surface sigma is said to be a surface sigma regular of class C n, regular of class C n. Only on regular surface you will be able to find out derivatives. A point P on a surface sigma is said to be regular of class C n if R 1 cross R 2 at the point P is non-zero. Okay, not only at the point P, in fact, on a neighborhood of P. This is non-zero in a neighborhood of P. This is non-zero. Okay. And in this case, I will say that the parameterization is regular around P. Okay. So, this is the important condition for regularity. So, for regularity of the surface, we will be assuming that all derivatives up to order n, partial derivatives exist, and the cross product of the basic tangent vector r 1 cross r 2 is non-zero. If this happens at every point, we will say the surface is regular. All right. Okay. If r 1 cross r 2 at some point becomes 0, then we say that the point is a singular point. If at P, if at some point Q r 1 cross r 2 equal to 0 vector, then we say that Q is a singularity. Then Q is called a singularity of the parametrization, is called the singularity of the parametrization. All right. So, this is about the singularity. Okay. Now, in Cartesian coordinate, how would you look at the singularity and regular points? So, let me this in fact is a topological condition. What happens, you will notice a little later that r 1 cross r 2 is a vector which is perpendicular to the surface. Okay. So, what we are demanding that we must be able to erect a normal at that point, okay, because if there are edges and other kind of thing, then you will not be able to erect a normal. Okay. So, this is the requirement for finding the normal, but normal I will be talking about little later. We use the word regular, okay, and this is equivalent to smoothness. It's smoothness of class C n, differentiable up to class C n. All right. Okay. Now, regularity in terms of the component. So, start with a surface r equal to r of u 1 u 2. And suppose the components are x, y and z. Now, r 1, if I ask you compute r 1, so r 1 for this surface will be del r upon del u1 by definition. So, what I will be doing? I will be differentiating the components of the vector with respect to u1. So, this is del x over del u1, del y over del u1, del z over del u1. You can also denote these things by x1, y1, z1. This will remain our convention, that whenever we put 1 as a suffix, we would be meaning it as a derivative with respect to the first variable. Similarly, r2 means derivative of r with respect to u2, that is del x over del u2, del y over del u2, del z over del u2, that you can write as x2, y2 and z2. Now, you can compute the cross product of r1 and r2 in a usual manner. It will be the determinant I, j, k in the first row, components of r1 over here, that is x1, y1, z1, x2, y2, z2. Okay. So, this will look like what? It will look like y1 z2, or I would prefer to write it like this. Del y1, del y upon del u1, this is y1, del z1 upon del z upon del u1, then del y upon del u2, del z over del u2 into I. In place of I will put a comma. Okay. Then minus times del x upon del u1, del z upon del u1, and then del x upon del u2, del z upon del u2 with a minus sign, and this is the j component of the vector, and lastly the k component will be another 2 by 2 determinant that will be del x upon del u1, del y upon del u1, del x upon del u2, del y over del u2. This is the vector r1 cross r2, whose components are these Jacobians. Okay. And now, if you are demanding that this vector should be non-zero, then this will be a non-zero when at least one of the Jacobian is non-zero. And in short, there is a shorter notation for these Jacobians. We usually denote this by del y z upon del u1 u2. This Jacobian is denoted by del x z upon del u1 u2, and the last one is del x y over del u1 u2. So, a point will be a regular point if at least one of the Jacobian is non-zero at that point. So, this is the conclusion. a point. So, this is the conclusion. A point P on a surface is a regular point if and only if at least one of the Jacobians namely del y z upon del u1 u2, del x z upon del u1 u2 and del x y upon del u1 u2. At least one of the Jacobians is non-zero at P. Okay. So, you can check whether a given point on a surface is a regular point or not. Okay. And the next thing is you can also write down an equation in the implicit form for a surface. So, you have seen in your earlier classes that a surface is represented by a vector, by a function of 3 variables. A surface, or I am talking about implicit equation of a surface. If I have a function of 3 variable f of 3 variable x, y, z, then in equation of this type, the equation of this type represents a surface, in R3 if one of the partial derivatives of f, at least one of them, is non-zero. If at least one of the partial derivatives of f, namely what are the partial derivatives of f? We denote them by the symbol f x, f y, f z. Okay. So, one of these partial derivative is non-zero. Then only such an equation will represent a surface, otherwise you can't get a surface from such an equation. Now, what happens is if f z is non-zero, for example, then there is a famous theorem called implicit function theorem. Then by implicit function theorem, we can write, if you call it number 1, by implicit function theorem, equation 1 can be written as z equal to f of x y. That means, you can get hold of a function small f such that the variable z will be explicitly related with x and y as a function of x and y. Okay, so, what I am saying over here, that equation 1 and 2 represent the same surface, and this happens when at least f z is non-zero. Similarly, if f y is non-zero, you will be able to express y as a function of x and z, etc. All right. Okay. Now, you can write down for such a equation the parametric representation. Now, we can also write a parametric equation of the above surface. How it is done? If I take x as parameter number 1, y as parameter number 2, then the vector valued function will be given by r equal to x y f of x y. So, x and y are the two parameters. Here x and y are the two parameters of the surface. So, if one of the partial derivative of capital F is non-zero, you can convert its equation into explicit form. This is known as explicit form of the equation, and this is the parametric form of the equation. So, you can convert it into any of the form. Now, with regard to the regularity of the surface, what I will be doing, I will be looking at R 1 cross R 2. Okay. So, from number 3, this is the third representation. So, from 3, we have, so I am saying x and y are the two parameters. So, R 1 means del r over del x. So, that will give me del x over del x means 1, del y over del x means 0, del f upon del x means you can call it del z upon del x also. Okay. Because z equal to f of x y. So, you can also write down del z upon del x, and R 2 also I can compute from here. R 2 will be equal to 0, 1 and del z over del y, and therefore, R 1 cross R 2 I can compute. So, this will give me R 1 cross R 2. Okay, R 1 cross R 2, you can take the cross product of these two vectors. So, this will be what? So, this will be 1 0 del z over del x and 0 1 del z over del y. So, minus del z over del x and then minus del z over del y and then 1. So, that is the cross product of the two vectors. This is always non-zero, because even if these two derivatives are 0, this will be non-zero vector, and therefore, the parameterization which you have obtained here is a regular parameterization. So, this confirms that the parameterization is regular, that is the parameterization is regular. Okay. These equations later in our next lecture.